In the last video, we talked about what it meant for a graph to be connected, and we said that a graph is connected if between any pair of vertices, there's a path between them. You can get from one to the other by following edges. Okay, and so theorem 1.3.2 tells us that if you have a graph G and it has at least 3 vertices, so the order is 3 or more, and suppose that G contains at least 2 distinct vertices, call them U and V, such that G minus U is connected and G minus V is connected. In other words, if you delete U and all of its adjacent edges, or incident edges, I should say, you're left with a connected graph. And also, if you start with G and you delete V and all of its incident edges, then you're left with a connected graph. If this is the case, if those 2 vertices exist, then you can conclude that G is connected. I'm not going to go through the proof here. The proof's in the notes and we can talk about it in class. But it's a good thing to think about whether or not the converse of this is true as well. And so this kind of gets at the idea of subgraphs of a graph, and in particular looking for connected components of a subgraph. Right? If we look up here at this graph G, this wasn't a connected graph because it has this part here that's connected, A, D, and C, there's paths between them, and then B and E, there's a path between them, but there's no way to get, let's say, from B to A, D, or C, right? This has a connected subgraph, though. If you just look at the subgraph that's generated by picking out the vertices A, D, and C, this gives you a connected subgraph. Similarly, you've got this other subgraph with just B and E that's connected as well. If we look at those sort of maximally connected subgraphs, they form what we call components of a graph. So we say that a connected subgraph of G is a component if it's not a proper subgraph of any other connected subgraph. In other words, if it's sort of the largest possible connected subgraph you could have using those vertices. So let's look at another example. This is a disconnected graph because, for instance, there's no way to get from C to any other vertex. Right? There's no way to get from D to E or from A to G. So this is a disconnected graph. But if we look at the connected components of it, or the connected subgraphs, we get this sort of triangular part here, right? This triangular part here, G, E, and B. This would be one component of the graph. Then we get this sort of L-shaped graph here, A, F, and D. This is another component. And finally, we get this single vertex off to the side here. This is a third component. So there's 3 components to this graph. And you can think about them as the graphs, or the induced subgraphs generated by A, F, and D, by G, E, and B, and finally by just C. And you'll notice that the components of this graph are going to partition the vertices of G. In other words, it splits it up into subsets that are disjoint and that together make up the entire graph. In other words, all of the vertices are going to have to fall into one of these partitions, right? One of these connected components. Okay, and anytime you have sort of some set being partitioned based on some sort of a rule, it's natural to wonder if there's some equivalence relation behind it. And in fact, there is. So theorem 1.3.3 states that if G is a graph and we define a relation R on the vertices of the graph by saying U is related to V if and only if U and V are connected. Again, connected doesn't mean adjacent, it just means there's a path between them, not necessarily an edge. In other words, U and V are related to each other by this relation if they're on the same component. Then we can prove that this is in fact an equivalence relation. All right, just as a reminder, if we're not familiar or if it's been a while, sometimes we write a relation as a set of ordered pairs. So you might be familiar with seeing notation like this instead. This is just a shorthand way of saying U and V satisfy this relation. All right, so let's prove that this is actually an equivalence relation. So there's 3 things that we need to show here. We need to show that this relation is, let's see, we've got reflexive, then symmetric and transitive. But let's start with reflexive. So to show that a relation is reflexive, we need to show that for every vertex, little v, in the vertex set of the graph, that vertex v is related to itself according to this relation. In other words, v is connected to v. In other words, there's a path from v to v. Well, this is sort of trivially true. If you pick a vertex v, there's a trivial path from v to v. There is a trivial path of length 0. We write it as v to v. Therefore, v is related to itself through this relation for every possible vertex in our graph, and so R is reflexive. All right, that's part 1 of an equivalence relation. Part 2 is we have to show that this relation is symmetric. In other words, we need to show, this time we start with 2 arbitrary vertices, let's say for all v and w in the vertex set of our graph. We need to show that if v is related to w, then w is related to v. All right, if v comma w is in this relation, then w comma v is in this relation. In other words, if v is connected to w, then w is connected to v. And of course this is true, right? Assume for arbitrary vertices u and v, or sorry, v and w, that v is connected to w. This means that there's a path from v to w. So let's say p from v, we'll call that v naught, v1, all the way to vk. Right, starting at v, which we're calling v naught, and ending at vk, which we're calling w. This is a path in our graph G. We want to show that w is related to v, well, we just reverse that path. Right, read this path backwards and you'll get yourself a path from w to v. In other words, if there is a path from v to w, you can follow that same path backwards and get from w to v. Let's call this p prime, which is defined by vk all the way down to v0 is a w to v path. So we have that w is related to v, thus our relation is symmetric. And finally, we have to show that this relation is transitive. To show that a relation is transitive, we must show that for any arbitrary, let's say u, v, and w in our vertex set, if u is related to v and v is related to w, then we have to be able to conclude that u is related to w. All right, so think about what this means here. If u is related to v and v is related to w, so assume u is related to v and v is related to w, what that means is there's some path in our graph connecting u to v. Right, I don't know what it looks like, but there's some path from u to v. And then we also know that there's a path from v to w. That's what this says. There's a path from v to w. So is there a path from u to w? Sure, right? Just sort of put these two paths together, right? So if we join together the u to v path with the v to w path, we get a u to w path. Well, okay, I'm sort of sweeping some things under the rugs here. We don't necessarily get a u to w path because it's possible that some of these vertices that I've drawn here actually end up getting repeated in our v to w path, right? So for example, I don't know, right here, u, v, w, there's a u to v path, there's a v to w path, but if we just put those two together, we'd get u, v, or u, w, v, w, which is not technically a path, it's a walk. But that's okay, right? Because we proved in the last video, we called it theorem 1.3.1, that if there is a u to w walk, then there must also be a u to w path, right? We get a u to w walk. So by theorem 1.3.1, there is a some u to w path. So u is in fact related to w as desired, and so r is transitive. Right? So since we've proven that this relation is reflexive, symmetric, and transitive, that's what it means to show this as an equivalence relation, and so we're done. Okay. Now, this sort of idea of getting from one vertex to another leads to thinking about what's sort of the most efficient way to do that. And so we define the distance between two vertices in a graph as the shortest possible length out of all the different paths in that graph. Right, so the distance between u and v is the length of the shortest path connecting u to v. And we use notation duv to denote the distance between u and v. And if you have a path of shortest possible distance, we call that path a geodesic. So let's look at an example here. There's lots of different paths here from A to F. Right, remember, paths means no repeated vertices or edges. So a long kind of silly path would be something like A to D to B to C to E to F. Right, A, D, B, C, E, F. That's a lot longer than necessary, but it does get you from A to F. If we want the distance between A to F, though, we want the shortest possible path. So we could try to list out all the different paths, but actually we can see that there's a pretty short path just by going from A to E to F. This is length 2 because there's only 2 edges here, A to E, E to F. I'll highlight that. All right, we've got A to E, then we've got E to F. So this is a length 2 path, and the only shorter path would be a length 1 path. That would just be an edge from A to F, but there is no edge from A to F. They're not adjacent in the graph. So we know that this path that I've highlighted is the shortest possible path, and so we can say that the distance between A to F is going to be 2, because it's the shortest path between A and F, and we call this path AEF is called a to F geodesic, because it's an example of the shortest way to get from A to F. All right, let's see. So one important thing to note here is that if u and v are vertices in your graph, and if G is a connected graph of order n, then there has to be some distance between u to v, right? If they're connected, there's some path between them, so there's a shortest path. That shortest path is going to have some distance. And so it has to be somewhere between 0, if u is equal to v, that would have the trivial path from u to v, and the maximum possible distance between them that you could have would be n minus 1, right? Because the largest your graph could be would be if you visited every single vertex in your graph. If you visited all 9 vertices, that paths would have length n minus 1. So the distance between those vertices is always somewhere between 0 and n minus 1, where n is the order of the graph. But if G is a disconnected graph, right, if they're not connected, right, something like this is a disconnected graph, then the distance between, say, A and B here is not defined, because the distance is the length of the shortest path, but there's no paths between A and B. And so there must exist vertices A and B in your graph such that the distance between A and B is undefined. Okay. But if your graph is connected, then we can sort of look at all the different possible distances between any pair of vertices. And if we look for the largest possible distance, we would call it the diameter of the graph. So essentially the diameter of the graph is going to describe the longest, shortest path. Right? Look at all the possible shortest path between any pairs of vertices. The longest such distance is going to be the diameter of the graph. All right, so if we wanted to find the diameter of this graph, we can sort of eliminate any pair of vertices that are adjacent to each other, right? The distance between, say, S and T is just 1 because they're adjacent. The shortest path is length 1. The distance between S and V is just 1. The distance between S and W is just 1. Okay, I don't actually want to list them all out here, so we want to start thinking to ourselves, what's sort of the longest possible path that you would have to take between pairs of vertices in the graph, right? It looks like Q is kind of farthest away. If you wanted to get from Q to a vertex over here, you'd have to pass through U, and you'd have to pass through R. You'd have to pass through either W or T to get to S or to V. So it seems like maybe the longest possible path would be, the longest possible shortest path would be V, T, R, U, Q. Is that right? Let's see, the distance from V to Q would be 1, 2, 3, 4. Similarly, the distance between S and Q would be S, so 1, 2, 3, 4 also. Right, but there's no vertices that are distance 5 apart. So the maximum possible diameter or distance between any pair of vertices seems to be 4. So we would say that the diameter of this graph is 4. Right, the diameter is sort of how spread out is it, right? If you wanted to find the shortest path between any pair of vertices, what's the furthest you'd have to go? Okay, so just to wrap up this section, a couple more points. In the exercises, you can think a little bit about this problem. This is the converse of theorem 1.3.2. It says if G is connected of order at least 3, and G contains 2 distinct vertices, or can we conclude that G contains 2 distinct vertices such that G minus U and G minus V are both connected? This is something to try to prove. And the last thing to consider has to do with the complement of a graph. So just as a quick definition, in the warm-up problem you saw something that hinted at this idea of a graph complement. The complement of a graph G, which we denote the complement G with a bar on top, G bar, is the graph that has the same vertex set as G, but it has sort of the opposite edge set. So we define the edge set E bar by saying it's the set of all edges UV such that UV is not an edge in G. Right, so as an example, if this is our graph G, it has vertex set 1, 2, 3, 4, and it has these 2 edges, 1 to 2 and 3 to 4. Then the complement of this graph would be 1, 2, 3, 4. It has to have the same vertex set, but we're only going to include an edge in this graph if it's not an edge here. So 1 to 3 is not an edge in G, which means it is going to be an edge in G bar. 2 to 4 is not an edge in G, so it is an edge in G bar. Similarly, 1 to 4 and 2 to 3 are not edges in G, so they will be an edge in G bar. But we take edges 1 to 2 and 3 to 4 out, right? So it's really just the exact opposite of the edge set of G. Okay, and so again, another kind of nice thing to think about is the relationship between graph complements and connectivity in a graph. So you'll see some problems in the exercises that get at those ideas.